All right, welcome to The Explainer. Today, we're plugging right into your body's most complex and, honestly, most vital network, the nervous system. We're going to break down how this incredible biological wiring uses these tiny electrical signals to create, well, every single thought, feeling, and action you've ever had. So let's start with this, because this quote really gets to the heart of it. It sounds like something out of science fiction, right? But it's shockingly close to how your nervous system actually works. Just think about that for a second. A single, simple electrical signal is behind everything, from feeling the warmth of the sun to figuring out a complex problem. It's wild. And here's where it gets even crazier. That signal, that nerve impulse, it's always the same. It fires with the exact same strength and at the exact same speed every single time. The only thing your neurons can change is the frequency, how often they fire that pulse. It's like a biological Morse code, just a stream of on-off signals that your brain somehow interprets into the entire rich experience of being alive. So, how does this whole system manage to pull off this incredible feat? I mean, how does it use such a simple code for such complex messages? Well, it all comes down to a constant, lightning-fast loop of activity. It's really all about this constant three-step process. First step is sensation. Your body is constantly gathering information from the world around you and from inside you. Step 2 is integration. Your brain takes all that info, makes sense of it, and decides what to do. And finally, step 3, response. Your brain sends out a command to make something happen. You sense, you process, you respond. Every second of every day. Now, to handle all of that information traffic without getting completely overwhelmed, the whole system is brilliantly organized into two main divisions that are always talking to each other. On one hand, you have your command center, the central nervous system, or CNS. That's the big boss, your brain and spinal cord, all safely tucked away inside your skull and spine. Then you have the peripheral nervous system, the PNS. And that's basically all the wiring. It's the massive network of nerves branching out from the center, connecting the command hub to every single part of your body. Okay, so let's zoom way, way in. We're going to go from this huge network down to the microscopic level and meet the actual cells that make all this high-speed chatting possible. And the absolute star of the show, of course, is the neuron. You can think of its dendrites as its ears, always listening for signals coming in from other cells. The cell body is kind of the neuron's headquarters, keeping everything running. And then there's the long axon, which acts like a mouth, sending the signal onward to the next cell in the line. But here's the thing. Neurons don't do it alone. Not even close. They have this massive support team called glial cells. In fact, you have more glial cells than you have neurons. These are the real unsung heroes. They do everything from tidying up the environment to wrapping axons in insulation so they can signal faster. They even act as the brain's personal security and immune system. They're the essential crew that keeps the whole show on the road. All right, now for the main event. Let's get to the climax of our story, the electrical signal itself. It's this dramatic, explosive little event called the action potential. To really get this, you have to think of your body as being just full of tiny biological batteries. I'm serious. Your cell membranes work really hard to keep positive and negative electrical charges separated. And by doing that, they build up this stored energy, this potential, just waiting to be unleashed. So when a neuron is just sitting there, waiting for a signal, it's in what we call its resting state. It has a resting membrane potential. Special pumps are working nonstop to make sure the inside of the cell stays electrically negative compared to the outside. This makes the neuron polarized. It's like a tiny, charged-up battery just waiting for the green light. And we can actually measure that charge. It's a real number. The inside of a neuron that's just resting sits at about -70 millivolts compared to the outside. That's its baseline. That's its ready-to-go state. But what happens when a signal comes in? Well, if that signal is strong enough to push the internal charge up to a certain tipping point, it triggers an unstoppable chain reaction. And this is key. It's all or nothing. The neuron either fires completely or it doesn't fire at all. There is no in-between. And that tipping point, that point of no return, it's this magic number, -55 millivolts. As soon as the inside of that neuron hits that charge, that's it. There's no stopping it. The action potential is on its way. Hitting that threshold kicks off this incredibly fast three-act play. First, depolarization. Tiny gates fly open and a flood of positive sodium ions rushes into the cell, making the inside suddenly positive. That's the spark. Then, just as fast, repolarization begins. Those gates snap shut, and another set opens to let positive potassium ions rush out, bringing the charge plummeting back down. It even overshoots a little bit. That's hyperpolarization, before everything resets. This whole electrical cascade is the action potential, and it happens in 1,000th of a second. So, how does this spark travel down the axon? Well, in some neurons, the unmyelinated ones, it moves like a continuous wave. It's like lighting a fuse. The spark in one section triggers a spark in the very next section, and so on all the way down. It works, but it's not exactly a speed demon. But for real speed, you need myelin. That's the fatty insulation made by our friends, the glial cells. It stops the electrical signal from leaking out. So instead of a slow burn, the action potential basically leaps from one gap in the myelin to the next. This saltatory conduction, which literally means leaping, is unbelievably fast. It lets messages cross your body almost instantly. Okay, so the signal is zipping down the neuron at incredible speed. But what happens when it gets to the end? How does it make the jump to the next cell? Well, it has to cross this tiny, tiny space called the synaptic gap. Now, that electrical pulse can't just jump across the gap, so it does something really clever. It switches from an electrical message to a chemical one. When the action potential arrives, it triggers the release of these little chemical messengers called neurotransmitters. They float across the tiny gap, dock onto the next neuron, and deliver their simple message, fire. Or sometimes don't fire. And all of this whole incredible process, brings us to one final, just mind-bending question. We've seen that the signal itself, the action potential, is always the same. It's a simple on or off pulse. So how? How does your brain take that one single, uniform message and translate it into the impossibly rich, complex, and infinite variety of human experience?